I thank you for clicking in, and on behalf of the Aircraft Engine Historical Society, my name is Tom Fay, and today's topic is the radio-controlled aerial gunnery targets of World War II. These are the four radio-controlled gunnery targets that will be described in today's video. The A-2 OQ-2 RP-4 aircraft in the upper left was first, followed by the OQ-2A, the OQ-3, and lastly the OQ-14. I will mention now that these four aircraft, as well as all of the aircraft described in this presentation, are all controlled by line of sight. They have no autonomous or over-the-horizon control capability. They have to be seen to be flown. The first truly successful radio-controlled gunnery target was the Fairy Queen. A large biplane on floats, it was powered by a 570 horsepower Napier Lion engine. 3 of these aircraft were built, 2 failed on launch, but the third aircraft flew for 9 minutes from the Valiant in September of 1932 under radio control. This third aircraft was relaunched in January of 1933 in the Mediterranean, where the ships of the home fleet tried for an hour to shoot it down. It was recovered unscathed. This was an alarming wake-up call to those that believed that the then present-day capabilities of anti-aircraft gunnery were sufficient to protect the naval warships from aerial attack. The early American experiments in radio-controlled flight began with the Curtiss N9 Wild Goose, which completed a successful radio-controlled flight in September of 1924. However, upon landing, a float ruptured, the aircraft sank, and the program was terminated due to technological immaturity and lack of funding. In the 1937 to 1939 time frame, Curtiss A3 aircraft were used, and these were controlled from either the ground or via a chase plane. The Stearman Hammond YH-1 had its first remotely piloted flight in November of 1937 and ended its days as a gunnery target in the summer of 1938. Douglas A-4 aircraft, of which 15 were modified in the 1940 time frame, also served experimental radio control flight. The first mass-produced radio-controlled aerial target was the de Havilland DH-82B Queen Bee, starting in 1935. This was a full-size aircraft with a 29-foot wingspan. In the early days, it was flown from floats and had a 70-mile-per-hour cruise speed. Almost 500 of these targets were manufactured, and actuation was by pneumatic servos. Of note is that all of the full-size aircraft mentioned thus far were either land-based tri-gear aircraft or seaplanes. This was due to the slow-moving flight controls of the time, which made takeoff of a tail dragger very difficult. Seaplanes always had a very long runway and could take off directly into the wind. Germany was also experimenting with radio-controlled target aircraft before World War II. Dr. Fritz Goslau of the Argus Motor Works began in 1937 working on a small, uncontrolled aerial target for use in training flak crews. This went on to be developed into a larger, radio-controlled aircraft powered by a 7-horsepower engine with a generator drive to provide electricity to the electronics and recovered by parachute. The first flight of this aircraft was in May of 1939. The Luftwaffe ordered 100 of these gunnery targets, and some were equipped with cameras. And now on to the American pioneers of the subscale aerial gunnery target history. Reginald Denny was a British-born screen actor and World War I veteran who had an interest in model aviation owned a hobby shop in Hollywood, California, and whose vision was to build radio-controlled aerial gunnery target aircraft for the U.S. military. Denny hired Kenneth Case, an electrical engineer in the early 1930s, to help him advance his ideas for radio-controlled model aircraft. Caltech graduate engineer and former Kinner, Vultee, and Lockheed employee Walter Ryder was already designing and building model engines for Denny, and he embarked on the target drone program in August of 1937. Paul Whittier was an entrepreneur, financier, and a partner with Reginald Denny in Denny Industries. The first aircraft built by the Denny team was the RP-1 in 1935. RP stood for radio plane. It had a 9-foot wingspan and was of typical wood construction. It used a 2.5 horsepower engine designed and built by Walter Ryder using parts from an Evinrude outboard motor. When first flown in November-December of 1937 at Fort MacArthur for Colonel Teal of the Coastal Artillery Command, it had only a short flight, no altitude gain, and crashed. However, Colonel Teal was impressed and encouraged them to carry on. The follow-on aircraft to the RP-1 was the RP-2. It used the same engine as the RP-1 but had 1 additional foot of wingspan. It was demonstrated to the U.S. Army in February of 1938. It had a successful takeoff from the ground and flew to approximately 200 feet of altitude, including a few slow turns, but a radio failure resulted in a terminal crash. Regardless, Colonel Teal was further encouraged, and a contract was signed with the U.S. Army for $18,000, which is equivalent to $328,000 in modern currency, to provide 3 experimental aerial targets within 1 year. The next aircraft in development was the Radio Plane 3, the RP-3. It now had a 12-foot wingspan. Its boxy fuselage was constructed of welded steel tube, had a tricycle landing gear, was launched by catapult, and recovered by a patented parachute system. It flew at 50 miles an hour. Kenneth Case is shown here, and the red arrow shows the parachute attached to the parachute hatch, with the patent shown on the right. The RP-3 was flown at March Field in Riverside, California during 1938. Controllability issues, especially at takeoff due to engine torque and the low slipstream over the control surfaces, resulted in many crashes. The blue arrow indicates that the parachute is still in place, so this aircraft likely crashed at takeoff. The control system utilized a telephone dial system, and only one function for the control could be operated at one time. So it was either up elevator, down elevator, right rudder, left rudder, and a button for the parachute. There was no throttle, and there were no ailerons. To control the aircraft, you had to select a function, say up elevator. You would turn the dial, let it go. The elevator would travel up until you stopped it, which required the use of the stop dial. The elevator would stay in that position until you used the down elevator function to move the elevator down, and then the stop function to stop it when it got to the position that you wanted. This was an acquired taste and rather difficult, but it was the technology of the times. Eventually, the team decided to go to a counter-rotating propeller system to address the torque problem and a joystick control. This next version of the target, designated the RP-4, used a 2AC-10 Sidewinder engine designed and built by Walter Ryder. This had counter-rotating propellers, meaning the propellers spun in opposite directions from each other, two-cylinder, two-stroke rotary valve, which was built in two versions, both simultaneously firing and alternate firing. The prop shafts used bevel gears to place the propellers 15 inches apart. The propellers themselves were 24 inches in diameter, and they were geared such to avoid interference with each other. This photo shows the RP-4 mounted on the catapult at Muroc Dry Lake during the spring of 1939. It is shown with the two SC-10 engine simultaneously firing. It has the cylinders pointing both up and down. It has a wingspan of 12 feet, a wing chord of 12 inches. It flew at about 70 miles an hour with a radio range of about 800 feet. It utilized a 20-foot diameter parachute and carried about 3/4 gallons of fuel. Compliments of the archives of the AUVM. Here is a front and rear view of the Ryder 2AC-10 Sidewinder engine. The side-by-side cylinder configuration was ultimately chosen as it had less vibration than the simultaneously firing configuration. Ignition was provided by a 4.5-volt dry cell battery. The propellers were indexed on their hubs with the phasing shown in this photograph. This minimized both the width and the weight of the engine and provided non-interference of the propeller arcs. Additional testing of the RP-4 at Muroc during the spring of 1939 revealed insufficient strength of the catapult so that the aircraft was not at a safe flying speed when it left the catapult, and getting the proper trim for center of gravity, incidence, thrust line, rudder, and elevator throws, etc., before the aircraft took off. The very clever team came up with a poor man's wind tunnel, which was a 1930 LaSalle rigged with a boom off to the side, which had a trapeze to capture the full-size target drone to evaluate lift, drag, trim, and airspeed. The RP-4 could move fore and aft 1 foot and up and down as well. The elevator was trimmable from the car. So this allowed the car to maintain a certain speed, and different combinations of trim and control movement could be evaluated. Through clever engineering and determination of the team, the RP-4 was successfully flown at Muroc Dry Lake in May of 1939. All three RP-4 aircraft were successfully flown and recovered in front of U.S. Army representatives on May 3rd of 1939. These three aircraft were shipped the next day to Wright Field in Ohio. One has to remember this is May of 1939. World War II started in Europe on September 1st of 1939, and the U.S. did not enter the war till after December 7th, 1941. The radio plane company to produce these drone aircraft was incorporated in the fall of 1939.
May have been capable of causing itself. By the 1930s, when this little target drone was developed, one of the bug's major deficiencies, its lack of guidance, was being looked at. Like today's model planes, the aircraft obeyed a handheld radio control unit. Interestingly, this unit employed a telephone dial to send the selected signal to the drone. As with all target drones, there was a balance between the disposability of the aircraft and the sophistication necessary for it to do its job. And in this case, as a target, the plane didn't really present a simulation of an enemy aircraft. However, ground troops could fire away at it and presumably learn something before it was blown away.
The manual of instructions for the Type A2 aerial target as well as the specification sheet for what's designated as the OQ2, are held in the collection of the Aviation Unmanned Vehicle Museum located in Caddo Mills, Texas. These sheets describe the specifications for these earliest of the radio-controlled gunnery target drones. The designation OQ2 was the later designation for the A2 after a change in nomenclature by the Army. OQ is the abbreviation for subscale unmanned aircraft. This photograph shows the A2 situated on the boom of the 1930 LaSalle. The only known surviving pieces of any of the first 53 aerial gunnery targets bought by the U.S. Army and designated A2 and then OQ2 are three of the very distinctive 24-inch propellers used on the Sidewinder 2AC-10 engines. In a recurring theme, the U.S. Army desired a faster, cheaper, and more easily produced gunnery target. Walter Reiter developed a new contra-rotating engine, the 3.3 cubic inch 1G3, but this was only about 1 horsepower, and I believe this engine was actually a proof of concept engine as a technology demonstrator for the contra-rotating gearbox. Eventually, a larger engine, the 2GS-17, was developed. The RP-5 prototype was completed in June of 1941, and the large-scale production of the RP-5A started in early 1942. All of the World War II target engines were two-cycle designs, meaning there is one power stroke for each single rotation of the crankshaft. The crankcase is a sealed chamber, and entry of the fuel-air mixture, shown in blue, is controlled by the rotary valve attached to the crankshaft. The rotary valve is shown in yellow. When the piston rises during the compression stroke, the air-fuel mixture is pulled through the carburetor, through the open rotary valve, and into the crankcase. When the piston descends during the power stroke, the crankcase is sealed by the rotary valve, the fuel-air mixture is compressed, and once the piston descends far enough to open first the exhaust ports within the cylinder wall, then the transfer ports, the fuel-air mixture expands from the crankcase into the top of the cylinder space. This forces the red exhaust gases out and renews the operating cycle. The engine is lubricated by the presence of oil in the air-fuel mixture. So here's the first mass-produced aerial gunnery target for the U.S. military. The radioplane RP-5A. RP-5A was the radioplane designation. The Air Corps called their aircraft the OQ-2A, and the U.S. Navy designated their aircraft the TDD-1 for Target Drone Denny. Wingspan was about 12 feet. The aircraft weighed about 108 pounds and flew at 85 miles an hour. The engine, which I'll describe shortly, made about 6.5 horsepower and drove concentric 26-inch diameter propellers in opposite directions. Like the versions before, only elevator and rudder were controlled by radio control. The engine ran wide open until it ran out of gas or was destroyed. 1.8 gallons of fuel would allow it to operate for 1 hour. With the increasing performance of the gunnery target drones, a new wind tunnel had to be developed. So the team purchased a 1941 Packard Senior V12 limousine of 150 horsepower, stripped a ton of weight off it, and rigged a trapeze off the front of the vehicle, and raced across the desert with the captive target drones at up to 120 miles an hour to again develop the required aerodynamics for proper operation and control of the drones. A total of almost 3,600 OQ-2A type aircraft were manufactured by Radioplane at the Metropolitan Airport in Van Nuys, California, and to a large degree at the Frankfurt Sailplane Company located in Joliet, Illinois. While less than 50 target aircraft were made in 1939, by 1945, 40 targets per day were being produced. The Ryder 2 GS-17 engines were manufactured by Ryder in Burbank, California, and the Herkimer Tool and Model Works in Herkimer, New York. The Army insisted in having at least 2 suppliers of the major components for this program. Norma Jean Doherty, age 19, worked at the Radioplane factory at the Metropolitan Airport in 1944. She went on to become Marilyn Monroe. Mass production of these gunnery target drones was a very labor-intensive operation. In these photographs taken from the Radioplane brochure, you can see some of the welding going on in the upper left, metalworking in the upper right, covering of the fuselage in the lower left, spraying and doping the components on the right. There was a large number of women in the workforce as this was wartime. Fabric cutting and sewing is shown in the upper left, while in the upper right is a lineup of welders fabricating various components for the fuselage. All of the fuselages and wings were covered, doped, and painted. The upper left shows a field jig for aligning a damaged fuselage. You can see the number of welds that are required, several of them rather large cluster welds. The lower left shows a lineup of drones ready for final packaging. And at the right, interestingly, the wings, fuselage, engine, propeller, and radio control system inside the fuselage can all be contained in a 2-foot by 2-foot by 10-foot plywood box. So here's a pre-production RP-5 without the fuselage covering. Going left to right are the 26-inch contra-rotating wood propellers driven by the 6-horsepower Ryder 2 GS-17 engine. A 1.8 gallon fuel tank resides just about at the center of gravity. The landing gear is sprung by bungee cords, telescoping gear with bungee cords. Further back is the radio receiver and antenna. The dark parachute is attached to a spring-loaded hatch, and below that is a battery box that slides on a tray. This allows the battery box to be moved fore or aft to get the proper center of gravity before launching. Further back is a single servo, dual function servo, which operates both the rudder and elevator. Again, there are no ailerons and there is no throttle. So this is what it takes to field an aerial gunnery target system. Going clockwise, the training unit consisted of 1 transmitter, 1 spare transmitter, 1 catapult, 12 aircraft, 1 officer, and 7 enlisted men. You can see the pilot with a joystick control and an audio headset, which I'll describe momentarily, a generator set with batteries, a dynamotor, which converts the electricity to the proper voltage and frequency to operate the radios, and the A2 catapult. The OQ-2A and subsequent World War II gunnery targets all used the same transmitter system. It was developed by the Army Signal Corps, operated on the 73 megahertz band, and it had no throttle or aileron function. Only one control function could be used at a time. The rudder was self-centering. The elevator was not self-centering, would stay where you left it, and this could act as a trim function. Each of the 4 control functions, up, down, left, right, had a distinct audible tone assigned to it, which provided information to the pilot for which function was being operated and for how long. A constant radio signal was sent to the aircraft either by control or as a fifth channel background signal. And as long as the aircraft was receiving a signal, a solenoid would hold the spring-loaded parachute door closed. Once this signal was interrupted, either by gunfire or failure, or by pressing the parachute button, after 2 seconds, the engine would be killed and the parachute would be released. The transmitter was made by the Doolittle Radio Company of Chicago, Illinois. This is the radio receiver for the gunnery targets. It contained 9 vacuum tubes and was made by the Bendix Aviation Company of Hollywood, California. The servo had 2 arms coming out which could move forward and backward for each. Basically, there were 2 6-volt reversible motors inside of this unit with a reduction gear train which would move push rods which moved the surfaces. The receiver, batteries, battery box, and cables weighed almost 16.5 pounds. The wings for the OQ-2A could be used on the left side or the right side because they did not have ailerons. There was a spar fitting in the center of each wing panel. The wings were attached to the fuselage by pins and clevises, and a strut was utilized to take the flight loads as well as to allow adjustment of wash-in or wash-out of the wing. The aircraft could be suspended by shackles, and the battery box moved forward or aft could get the proper center of gravity for flight. The A-2 catapult used to launch the gunnery targets was almost 38 feet long. It weighed almost 900 pounds, and the bungee shock cord system generated 700 pounds of tension to launch the aircraft. This was adequate to launch an aircraft weighing up to 143 pounds to 65 miles an hour coming off the end of the catapult. The catapults were built by the Montpelier Manufacturing Company of Princeton, Indiana. This is how the aircraft was mounted to the catapult car. The carriage had pins facing forward which engaged cylindrical fittings on the 2 landing gear struts as well as the center line of the fuselage airframe. A holdback device indicated by C kept everything in place until the cord was pulled for launch. This is an original OQ-2A airframe shown at Oshkosh a few years back. The wings are uncovered and you can see the lightning holes in the spruce ribs. You can also see the slots in the end of the starboard wing, and these engage clevises and were attached to the fuselage with pins, such that the left-hand panel and right-hand panel were fully interchangeable on the airframe. Also of note is the steel tube horizontal stabilizers and the vertical stabilizers. These assemblies are identical and can be moved from place to place, while the rudder and the elevator are individual assemblies. The open wings of this OQ-2A revealed inspection stamps as well as dates and a little bit of artwork done by Dottie on November 26 of 1943. The parachute for the 108-pound OQ-2A was 24 feet in diameter and made of Celanese rayon material. 2 ripcord pins were tethered to the fuselage such that when the spring-loaded door opened, these pins were removed from the pack and the parachute was pulled out with the help of the 3-foot diameter pilot chute. This parachute provided a 20 foot per second descent rate. This cutaway of the Ryder 2GS-17 engine shows it to be a 2-cylinder, 2-stroke rotary valve engine of simultaneous ignition. Bore was 2 1/4 inch by a stroke of 2 1/8 with a 4.1 actual dynamic compression ratio. This restored Ryder 2GS-17 engine was built in June of 1943. The data plate explains that 8 parts of 73 to 100 octane gasoline should be mixed with 1 part of 20 weight motor oil. The most common question regarding the Ryder 2GS17 engine is how was contra-rotation of the propellers achieved? Shown in the left-hand panel is the engine with the front cover of the gear case removed. The extended crankshaft also functions as the fore propeller shaft. Attached to the crankshaft is a large gear A, and the crankshaft turns in the counterclockwise direction. Gear A meshes with gear B and turns B in the clockwise direction. Gear B meshes with gear C and turns it in the counterclockwise direction. When you fold the gear case over onto the front of the engine, gear C interacts with gear D, and D is attached to the rear propeller hub, which is turned in a counterclockwise direction. The gear case is sealed from the power section of the engine and has its own supply of 70 weight gear oil. This is the rotary valve induction system for the Ryder 2GS17 engine. In the far right, you can see the rotary valve that has the pie-shaped cutout, which allows air-fuel mixture to be sucked up through the intake trunk at the appropriate time and into the crankcase. A bronze tail bearing has an oil-tight seal in the rear cover, and these engine castings are of a magnesium alloy. Like Walter Ryder's successful model engine designs, the 2GS17 used a battery, cam, and breaker point ignition system. Unique to the 2GS17 was a centrifugal advance similar to that used in vintage automobile engines, which would advance the ignition up to 20 degrees starting at 2,000 RPM. A dual coil was used which fired both spark plugs at the exact same time, and the whole system ran on a 6-volt ignition battery that could last up to 3 hours. This is the crankshaft of the 2GS17 engine. You can see that the 2 crank pins are offset end to end from each other. This geometry causes the power pulses to produce a rocking motion in yaw at up to 63 times per second at the rated 3,800 RPM of the engine. This required the use of rubber isolation engine mounts to prevent the self-destruction of both the electronics and the airframe. The propellers for the Ryder 2GS17 engine were 26 inches in diameter by 23 inches in pitch, weighed approximately 11 ounces each, and cost $4.38 each in 1943, which is the equivalent of $79 in 2024 dollars. The propellers were made by a number of producers, including Story, Ritz, Flotork, and Karpen. The OQ-2A went into production in early 1942, yet somehow 9 months later, the U.S. Army required that a 50-hour type test be done on a 6-horsepower engine used in a non-man-carrying aircraft that was designed to be shot down. The tests were performed in early 1943. They ran the engine at 4,200 RPM for 50 hours. I know it's hard to see some of the information here, but basically the engine made 2.8 horsepower at 3,000 RPM, 6.2 horsepower at 3,800 RPM, which is its rated horsepower, and 7.3 horsepower at 4,200 RPM. Here's some of the data showing the results at 6.2 horsepower. The crankcase temperature stabilized at 150 degrees Fahrenheit. The head temperature at the spark plug was 380 degrees Fahrenheit, and the engine used 8 pounds of fuel per hour. The Handbook of Service Instructions for the 2GS-17 engine states that great care must be taken to keep from being hurt by the propeller, as this engine is much quicker to accelerate than a larger aircraft engine. This is true. They also state that there is no danger of injury from the rear propeller. It adds only a mental hazard. This is not true. And an engine hit by gunfire might be expected to fail. The entire premise for the use of subscale target drone aircraft was that a subscale target flying at a 200-yard range, flying at 100 miles per hour, approximates the perspective of a full-size pursuit aircraft flying at 300 miles per hour, 500 yards distance from the gun, which simulates attack conditions through practically all flight attitudes. This is a selection of period photographs showing the drones in action. The upper left is the pilot with the field glasses and the headphones on, using the joystick controller. The right shows a unit on their way to training with the catapult, a number of drones inside the trailers. Lower left shows a TDD-1 on the USS New York, a battleship in September of 1943. And the right-hand photograph shows a TDD-1 coming off the catapult. There was a standardized process for the training of gunnery. The gunners are shown diagrammatically in the blue box, and they are firing upwards towards the top of the slides. The areas designated in red are the areas where the targets were allowed to be fired upon. The distance from the gunners was approximately 150 to 400 yards. The bullet tips were painted with different colors for different groups, and there was a metric for giving a score for the success of the various groups firing at the targets. Here are a couple of photographs showing the OQ-2A coming off the catapult at the top, and at the bottom is a TDD-1 on a short bungee catapult attached to the nose of an AVR fast patrol boat. You'll notice that the TDD-1 lacks landing gear. These period photographs show the varied outcome of gunnery training. Of note is the upper right-hand picture showing a bullet going across the cylinder, across the gear case, and out. This is a cylinder from an O-15-3 gunnery target drone engine, clearly showing bullet scars. An original packing slip dated April 27, 1943 gives insight to the true cost of an OQ-2A drone. Listed on the sheet is a cost of $1,256 in 1943, equivalent to about $23,000 in today's money. That price does not include government-furnished equipment, GFE, which was the radio equipment. As a frame of reference, a P-51 Mustang cost $59,000 in 1943, or about $1.1 million in today's dollars. So one P-51 Mustang was the equivalent to 47 OQ-2A drones. This film has no original audio and was likely shot at Fort Bliss outside of El Paso, Texas. It shows the OQ-2As being prepared for use, parachute being folded, which was then installed into the parachute hatch, and then the hatch was installed into the airframe. Off to the range they go. The catapult cart being winched back into position. This shows how slow the control surfaces moved. The rudder was self-centering when the stick was neutralized. The elevator was not, and thus once moved, it had to be moved back into a different position. The parachute button releases the parachute and kills the engine. The engine was started, the RPM checked, allowed to warm up for a minute or two, and then launched. Here are 5 tracked vehicles, each with a single .50 caliber machine gun. Aircraft coming directly at the guns. The normal loadout for a .50 caliber machine gun was 4 bullets plus 1 tracer round. The tracer rounds can be seen as shooting stars in this film. So that for every tracer round, there's 4 additional bullets coming out in roughly the same trajectory. The sky was absolutely filled with lead, and you can see that most of the gunners are shooting behind and perhaps too low at the target. With the fuel on board, it could fly for approximately 1 hour, and the batteries were good for about 3 hours of service before they needed to be changed. The aircraft was not shot down. Parachute button could be activated. The engine is killed. The parachute comes down. Plane descends at 20 feet per second. The landing gear was in part designed to simply absorb the shock loads to preserve the airframe, and in particular the propellers, and not designed to land in a traditional landing technique. A deceased gentleman named Norman Smith of Orlando, Florida, had acquired 2 OQ-2A aircraft and adapted them to modern flying by removing the parachute, adding a steerable tailwheel, a throttle carburetor, and a modern radio system. The flight weight was now 79 pounds versus roughly 100 pounds for the original item.
My name is Norman Smith. I'm from Orlando, Florida. This airplane is a World War II target plane that at that time it was called a radio plane.
On August 11, 1942, 3 TDD-1 gunnery targets were destroyed by 5-inch shells tipped with the ultra-top secret proximity fuse, also known as the VT or variable timing fuse, fired from the USS Cleveland off Tangier Island in Chesapeake Bay. The proximity fuse contains a miniaturized radar system in the nose cone that detonated the shell when it was 70 feet from the target. Gunnery target number 1 failed at launch. However, target 2, 3, and 4 were destroyed after 80 rounds, 4 rounds, and 8 rounds, respectively, during these trials. After this acceptance trial, the proximity fuse went into mass production, and it had its first combat success in January of 1943 off Guadalcanal. Over 22 million proximity fuses were produced during World War II. The next step in the target story was a faster, simpler radioplane OQ-3 aircraft. The Army didn't like the expense, weight, and complexity of the contraprops, so they experimented by attaching a large propeller on the foreshaft of the 2GS-7T and were able to fly it successfully. There was the torque problem. However, full rudder on takeoff and patience before aggressive flight control allowed adequate flight performance. So Walter Ryder designed the 015-3 engine and raised the compression ratio, removed the gearbox, so it had a single rotation 30-inch propeller, and it made 8 horsepower. This lighter, more powerful engine was used to power the OQ-3, also known as the TDD-2 in naval service. The weight of the aircraft went down to 97 pounds. The rate of climb was 1,500 feet per minute. The stall speed was only 35 miles per hour, and its top speed was 102 miles per hour. Radioplane and the Frankfurt Sailplane Company produced almost 13,000 OQ-3 TDD-2 targets for the U.S. military during World War II. This radioplane OQ-3 TDD-2 is in the collection of the AUVM in Caddo Mills, Texas. It is complete with the fuel tank, radio, servo, engine, etc. A real historic piece. This photograph shows the OQ-3 just about ready for launch and upon parachute recovery. These are period photographs of the TDD-2 in service in March of 1945 on the battleship the USS Wisconsin and also the USS Miami. This video has no audio, but you can see in color the TDD-2 being prepared for launch. He's adjusting the mixture to get the proper RPM on the engine. I suspect he was hard of hearing later in life. The launch officer. Off it goes. So focus on the upper left-hand part of this screen as we go along. Here you can see the tracer. The military sought even higher performance from the aerial gunnery targets, and this resulted in the radioplane RP-8A, or the OQ-14 for the Army and the TDD-3 in the Navy. The prototype was completed in July of 1944. The OQ-14 can be distinguished by the larger engine, the carburetor on top of the engine, and the intake for the carburetor facing backwards. About 9,400 of these aircraft were manufactured during World War II. The OQ-14 had similar dimensions as the previous drones, although they were beefed up. They had a 20 horsepower engine and they carried 3.5 gallons of fuel. The weight was now 134 pounds, but the speed was 140 miles per hour with a climb of 3,000 feet per minute. Because of the more powerful engine, the higher airspeeds, and the greater weight of the OQ-14, the structure of the aircraft needed strengthening. The wing ribs were now solid and had drag bracing shown in red inside of them. Thicker poplar plywood was used on the leading edge, larger diameter tubing for the rudder and elevator, and a much stronger servo to handle the higher aerodynamic loads. The Ryder designed 045-1 engine for the OQ-14 displays 747 cc's. It made 20 horsepower at 3,650 RPM. The engine used roller bearings for both ends of the crankshaft as well as both ends of the connecting rod, and a ball bearing to take the thrust loads from the propeller. The engine was manufactured by Ryder, Keycafer Corporation, and Manasco. Interestingly, the individual producers of the engine were allowed to make their own minor changes to some of the components for either efficiency or for economy. However, all of the parts between the manufacturers had to be completely interchangeable. This is a Kiekäfer 045-1 manufactured in 1945. This is the 045-1 engine during disassembly. In the lower left, you can see the roller element bearings inside of the rear cover. The lower right shows the rotary valve. The compression ratio was now 5.3 to 1 true dynamic compression ratio, and the fuel burn was 3.2 gallons per hour. The two photographs on the left show the back and front of the timer assembly. This could be manually rotated up to 30 degrees to give 30 degrees of advance to the ignition timing. The piston had two compression rings which were notched, and these notches engaged pins in the piston to prevent the rings from rotating in the bore. This shows the TDD-3 in operation with the Navy off the battleship USS Wisconsin, again in March of 1945. This is a TDD-3 off the catapult. These are photographs of a TDD-2 or TDD-3 being shot down off the escort carrier USS Macon Island in October of 1945. This video has no sound, but it shows OQ-14 in operation in El Paso, Texas. Onto the catapult it goes. And coming down by parachute into the scrub. This is a table of relevant summary data for the 4 aerial gunnery targets that served America during World War II. The aircraft weight doubled over those years, and the horsepower went up 4-fold. Target airspeed almost tripled, and the power loading was halved. Over 25,000 of these drones were generated during World War II at a cost of $30.7 million US dollars in 1945 currency, equivalent to about $540 million in today's currency. There were additional radioplane gunnery target drones that flew before the end of World War II but had not gone into production by the end of the war in August of 1945. The OQ-6 used an experimental 4-cylinder Reiter engine. It was capable of 168 miles per hour. The OQ-17 looked much more like an airplane than previous aircraft. It had an aluminum fuselage, and its first flight was in March of 1945. 430 were ultimately constructed in the 1946 time frame. The OQ-19, powered by a 60-horsepower 4-cylinder McCulloch engine, first flew in July of 1945, and this design went on to great success after World War II. To complete the story of the early drone program, Paul Whittier was uninterested in the production of military drones and dropped out of radio plane in 1939. Reginald Denny sold his hobby shop and the majority of his interest in what became radio plane also in 1939, but remained active in the field. Walter Ryder sold Ryder Manufacturing to Radioplane in 1945 and went on to other engineering endeavors. Radioplane was purchased by Northrop Aircraft in 1952 and became the Northrop Corporation Ventura Division in 1962. Radioplane, Northrop Ventura went on to design and build over 71,000 drones of increasing speed, capability, and complexity well into the middle 80s. This video was made possible by the contributions to history made by the individuals, institutions, and documents acknowledged here. For those interested in more technical information on the World War II gunnery target engines, please see www.enginehistory.org. And I thank you for your attention.